So in this video we are going to discuss the question in thermal physics which appeared in IIT-JAM 2012 examinations. Okay, the first question is, when the temperature of the body is doubled, the maximum value of its spectral energy density with respect to that at initial temperature would become. Okay, so as we know that the maximum spectral energy density, it's proportional to T power 4. Okay, so when temperature changes from T to 2T, so because intensity it's proportional to T power 4, so this implies I dash, which represents the intensity when temperature has changed to 2T. Okay, so this is proportional to 2T power 4. Okay, so this will be 16 times T power 4, or in other words you can say that the new spectral density, it will be equal to 16 times the previous spectral density. So therefore correct option here is C. So let's take a look at the next question. The statement is, a tiny dust particle of mass 1.4 into 10 power minus 11 kilogram. Okay, so this is given to us. Mass of the dust particle is 1.4 into 10 power minus 11. Okay, is floating in air at temperature 300 Kelvin. So temperature is given to us, it is 300 Kelvin. Okay, ignoring the gravity, its RMS speed in micrometer per second. Okay, so we have to determine what is VRMS. Okay, this is equal to what? Due to random collision with air molecule will be closest to, so we have to figure it out. Okay, so if you recall the expression for the root mean square speed, VRMS, that is equal to 3 kVt upon mass of the gas molecule. Okay, so this is equal to 3, and then the value of the Boltzmann constant, which is 1.38 into 10 power minus 23, and then multiply by the temperature 300 divided by the mass of the gas molecule, which is given to be 1.4 into 10 power minus 11 kg. Okay, and it's a square root. Okay, and if you evaluate it, it comes out to be equal to 30 into 10 power minus 6 meter per second, which is equal to 30 micrometer per second. So therefore C is the correct option here. So let's continue with the next question. The statement is, the PV diagram below represents an ideal monatomic gas cycle. So it's a monatomic gas which is ideal, okay, for 1 mole of a gas. Okay, so N is given to be 1 mole. Okay, in terms of gas constant R, calculate the temperature at point J, K, L, M. Okay, so at these 4 points we have to calculate the corresponding temperature. Also calculate the heat rejected and heat absorbed during the cycle. So that's the second part, and efficiency of the cycle. Okay, so let's continue with the first part. In the first part we will calculate the temperature at 4 different points. Okay, so for ideal gas, PV is equal to nRT, because N is given to be 1. So from here temperature, corresponding temperature, that is equal to PV upon R. Okay, so now at point J, so let's continue from J. At point J, let's call the temperature as Tj. Okay, so Tj is equal to the product of PV divided by R. So what is at point J, what is the pressure? It's 80 kilopascal. Okay, so that is P, that is 80 kilopascal, 80 into 10 power 3 Pascal. Okay, multiply by the corresponding volume. So what is the volume? It's 0.03, and it is in meter cube. Okay, so multiply by 0.03 divided by R. So if you do the multiplication, it will come out to be equal to 2400 divided by R. So that's the temperature at point J. Now at point K, let's call the corresponding temperature as Tk and apply the same equation. Okay, so Tk is equal to, at this point it's Pb, so at this point pressure is 160 kilopascal, so 160 into 10 power 3 multiply by the corresponding volume, which is 0.03 divided by R. Okay, so after doing the multiplication, it turns out to be equal to 4800 divided by R. Similarly, at point L, corresponding temperature is TL, which is PV. So pressure is 160 again, 160 kilopascal, 160 into 10 power 3 multiplied by the corresponding volume, which is 0.1. Okay, divided by R, and this is equal to 16,000 divided by R. So at point M, the temperature is Tm, and this is equal to Pv by R. Okay, what is pressure at point M? It is 80 kilopascal. Okay, so let me write it, 80 kilopascal, 80 into 10 power 3 multiplied by the corresponding volume, which is 0.1 divided by R, and this is equal to 8000 divided by R. Okay, now we have done one part, and now in order to calculate the efficiency, okay, we need to evaluate the total work done during the complete cycle. Okay, so let me call this as the part 2. So the total work done during cycle JKLM, and that is equal to the area bounded by this curve. Okay, so W, the work done, the total work done, that is equal to area of loop JKLM. Okay, so simply we have to plug in the information. So that is equal to change in pressure and change in volume, which is equal to 160 minus 80 multiply by 10 power 3. So this is the pressure change. Okay, 10 power 3, and then multiply by the delta B, the other arm of this rectangle, which is equal to 0.1 minus 0.03. Okay, and after doing the calculation, this will come out to be equal to 5600 joule. Okay, so this is the total work done during the complete process. Okay, now let's calculate the respective change in the heat during all these 4 steps. Okay, so we will continue from the step J to K. Okay, so J to K process, if you just take a look at this process, this is taking place at constant volume, so that means it is an isochoric process. So let's do the calculations here. Okay, I will call this as part 3. Okay, process JK, it is isochoric. Okay, so that means dV, that is equal to 0, which implies dW, that is equal to 0. So by applying the first law, so corresponding change in the heat, I call that dQ1, that is equal to du1 plus dW1, which will be 0. And what is du1? Because it's a constant volume process, so this will be du, that is equal to n Cv dt, because n it's given to be 1, so Cb for the monatomic gas it is 3 by 2 R. Okay, and the corresponding change in temperature, so therefore dQ1 will be 3 by 2 R, and then delta T. What is delta T? It is J to K, so that means Tk minus Tj. So because this temperature we have already determined, and Tk minus Tj, if you just substitute the values, so this will come out to equal to 3, this is 3 by 2 R multiplied by the Tk minus Tj, which is 2400 divided by R. Okay, if you just you can check it from here, tk minus tj. So you just simply take the difference between these two, then you will obtain the this answer. Okay, so this is nothing but this is equal to 3600 joule. Okay, now let's take the second step, which is process KL. Okay, process K to L. Okay, which is, let's take a look at the diagram. Process K to L, here this is at constant pressure, it's isobaric. Okay, isobaric process. So in isobaric process, the heat change involved, if we call this as dQ2, this is equal to NCP delta T, NCP dt. Okay, and N it is 1, so it is simply Cp dt. What is Cp? For an because it's a monatomic gas, so Cb, that is equal to 3 by 2 R. So Cp will be 3 by 2 R plus R, so that is equal to 5 by 2 R. Okay, so I will take it directly. So 5 by 2 R and dt. What is dt? It is temperature at point L minus temperature at point K. Temperature at the final point minus temperature at the initial point. Okay, so if you substitute the values of TL and TK, so then we obtain the following result. Okay, so this is equal to 5 by 2 R multiplied by 11,200 divided by R, and this is equal to 28,000 joule, that is dQ2. Okay, now process, the third step, process LM. It is isochoric, that is dV, that is equal to 0. So if I call this as dQ3, the heat change involved, that is equal to, here it is NCV dt. The next term will be 0. Okay, plus dW term, I mean. Okay, because dV is equal to 0. So this is equal to Cv, which is 3 by 2 R, N is 1 here, 3 by 2 R, and corresponding dt will be temperature at point M minus temperature at point L. Okay, and this will come out to be negative because the temperature at point L, so okay, this is higher than the temperature at point M, so difference will be negative. Okay, so this is equal to 3 by 2 R multiplied by the difference, which is minus 8,000 divided by R, and dQ3 it's negative, so that means during this step heat is rejected. Okay, and after doing the multiplication, and this is minus 12,000 joule. Okay, now similarly in the last step, which is process MJ, this is again isobaric process. Okay, so corresponding heat change, if I am calling that dQ4, that will be NCP dt, that is Cp because N is 1 and dt is what? Temperature at point J minus temperature at point M. Okay, so Cp is 5 by 2 R multiply by Tj minus Tm. Okay, so Tj minus Tm, that's again negative. Okay, so if you substitute the value of Tj and Tm, so we will obtain minus 5,600 divided by R, and after doing the multiplication, this is minus 14,000 joule. Okay, now the net heat absorbed during the entire process. So we have calculated all 4 different heat changes involved during the process. Now net heat absorbed during cycle, so I'm calling that Q absorbed, and that is equal to dQ1 plus dQ2, because only dQ1 and dQ2 they are positive quantities. Okay, dQ3 and dQ3 they are negative. Okay, and if you add these two quantities, it will come out to be equal to 31,600 joule. Okay, now what is the heat rejected? Heat rejected during cycle that is equal to Q rejected, and that is equal to dQ3 plus dQ4 because these are negative. Okay, and if you plug in this value we will obtain 26,000 joule. Now how the efficiency is defined? Efficiency is output divided by input. What is the output? That is the work done obtained, work done during the complete cycle divided by heat input, which is the Q absorbed. Okay, so what is the work done? We have already calculated the work done in the previous page. Yes, here. So work done we calculated to be equal to 5600 joule. Okay, so if you plug in that value here, that is 5600 joule divided by heat input, which is Q absorbed, which is 31,600 joule. Okay, so this will come out to be equal to 14 divided by 79. So that is our answer. So this way we have calculated all the parameters which were asked in the statement. Okay. So let's continue with next question. It is related to the entropy change calculation. So we are given a situation where 2 kg of a liquid with the given specific heat independent of temperature is heated from a temperature 200 Kelvin to 400 Kelvin. Okay, so we are given a situation where there is a temperature change. It's changing from T1 to T2, that is 200 Kelvin to 400 Kelvin. So which implies delta T, that is 200 Kelvin. Okay, either by either of the following two processes P1 and P2. Okay, in P1, process P1, bringing it in contact with the reservoir at 400 Kelvin. So in process P1, the system or the liquid is directly coming in contact with the one single reservoir which is at temperature 400 Kelvin, and in the second process P2, it is first it is coming in contact with the reservoir which is at 300 Kelvin, and till equilibrium is reached, and then bringing it in contact with the another reservoir which is at 400 Kelvin. Okay, so we have to change what is the objective? We have to calculate the change in entropy of the liquid and that of the universe in the process P1 and P2. Okay, neglect any change in the volume of the liquid. So in order to calculate the entropy of the universe, so that means we also need to calculate the entropy change of the reservoir, so that the collectively the entropy change of the liquid and entropy change of the reservoir, that will determine the net entropy change of the universe during these two different processes. Okay, so let's continue with the process P1 first. Okay, process P1. Okay, so we will calculate the entropy change for the liquid. Okay, so and if I call that as delta SL, that's the entropy change of liquid. So that is the, because temperature of the liquid is changing, so we will make use of the expression where temperature change is involved. So delta SL, that is equal to dQ by T, where temperature is changing from certain value T1 to T2. Now what is dQ? That is equal to mass of the liquid multiplied by its specific heat, and then ms delta T or dt upon T. Okay, from certain temperature T1 to T2. Okay, and when we substitute the value of this, the mass and the specific heat, mass is 2 kg and specific heat it's 2000 joule per Kelvin per kg. So after doing the multiplication, we will obtain a factor of 4 into 10 power 3. So this is coming from this product of these two quantities, and then dt upon T, where the temperature change from 200 to 400 Kelvin. Okay, so this will come out to be equal to, this is 4 into 10 power 3 ln T2 by T1. So when we do ln 400 by 200, that will give us a ln2 only. So I am writing here only ln2, and it is in joule per Kelvin. Okay, now similarly in process P2, so this was process P1, in process P2, So it is the liquid is heated in two stages. Okay, the first stage is initially temperature change from 200 Kelvin to 300 Kelvin, and then in the second stage the temperature changes from 300 Kelvin to 400 Kelvin. Okay, so therefore the corresponding entropy change of the liquid during these two step process, delta SL, that is equal to, again same expression will be used, but now the it's going to have two different expressions. Okay, but the product of M and S, that's going to be constant in both cases. Okay, so that is 4 into 10 power 3, that is ms, and then dt by t when temperature is changing from 200 to 300. Okay, plus now for the second process 4 into 10 power 3, now 300 to 400 dt by t. Okay, and this is equal to 4 into 10 power 3 ln 3 by 2, and this will be plus ln 4 by 3. Okay, so log a plus log b. So when we are having a situation like this, log a plus log b, that is equal to ln ab. Okay, so here we will have additional factor of log 4 by 3, ln 4 by 3. So what I'm doing is I am simply multiplying that factor here. Okay, so that will help us to solve it quickly. Okay, so this is 2. Okay, so that means this is equal to 4 into 10 power 3 ln 2 joule per Kelvin. Okay, now we have determined the entropy change of the liquid. Now we will determine the entropy change of the reservoir. Okay, so let's try to do this calculation. Entropy change of the reservoir. So when liquid is heated, so that means reservoir it's losing the energy. Okay, so that means a negative sign will come while evaluating the heat exchange involved during this process for the reservoir. Okay, so in process P1, what is the heat energy exchanged by the reservoir? Let me call this as delta Q1. So it is determined by from the material parameter of the liquid. Okay, so that is equal to, because the same amount of heat will be gained by the liquid, and for liquid it's going to be positive quantity, whereas for the reservoir it's going to be negative quantity. So this is equal to ms and dt, but now with negative sign because reservoir is losing the energy. So this is equal to minus 4 into 10 power 3 multiplied by the change in temperature, which is 200 Kelvin in the process P1, and that is equal to minus 8 into 10 power 5 joule. Okay, therefore the entropy change of the reservoir during process 1, that is equal to delta Q1 upon the temperature at which the reservoir is doing, or at which the reservoir is sharing that energy, and the temperature of the reservoir is 400. Okay, and this is equal to minus 8 into 10 power 5 divided by 400. Okay, and this is minus 2 into 10 power 3 joule per Kelvin. Now similarly for the process P2, now we have to do the similar calculation. Okay, because it's taking place in two different steps, so let me call the corresponding heat change delta Q2 and delta Q3, and delta Q2 again it's negative because the reservoir is losing the energy, minus ms, and corresponding change in temperature, that's 300 to 200. Or okay, so if you do the calculation, so this will be minus 4 into 10 power 5 joule, and similarly for the next step delta Q3 300 to 400, this will be minus ms 400 minus 300, that is equal to minus 4 into 10 power 5 joule. Okay, now the net entropy change of the reservoir during process P2, so let me call this as delta S R2 during process 2. Okay, so that is equal to delta Q2 upon the temperature of the reservoir, which is 300 in the first step, okay, plus delta Q3 upon the temperature of the reservoir, which is 400, okay. And after substituting the values of these two quantities, that is minus 4 into 10 power 5 upon 300 plus minus 4 into 10 power 5 divided by 400, okay. So after plugging these values, we obtain delta S R2. After solving, we obtain this is equal to minus 2.33 into 10 power 3 joule per Kelvin, okay. Now the net entropy change of the universe, okay. Entropy change of universe, okay. So in process 1, let's evaluate in process 1 where liquid is heated in one single step. So delta S universe will be delta S, the entropy change of the liquid in process 1, plus entropy change of the reservoir in process 1, okay. And if you substitute the values, so in during step 1, so delta SL, that is 4 into 10 power 3 ln2, okay. So that is equal to 4 into 10 power 3 ln2 plus the entropy change of the reservoir, it is negative minus 2 into 10 power 3. So after evaluating this quantity, it will come out to be equal to 7.72 into 10 power 2 joule per Kelvin, which is greater than 0, as it should be for an irreversible process, okay. Now let's calculate the entropy change of the universe for process 2. So delta S universe, that is equal to entropy change of the liquid in process 2 plus entropy change of the reservoir in process 2, okay. So substituting the value as we have obtained in previous page, 4 into 10 power 3 ln2 plus the entropy change of the reservoir in the process 2, 2.33 into 10 power 3. So this is what we obtained in the previous step, okay. So after doing the calculation, so this will come out to be equal to 4.42 into 10 power 2 joule per Kelvin. So this is our final answer. So let's continue with the next question. The statement is, for a liquid to vapor phase transition at temperature TTR, which of the following plots between specific gives free energy G and the temperature T is correct, okay. So before we arrive at some final conclusion, so let's try to understand how the entropy and Gibbs free energy, they are connected with each other, okay. So the relationship that connects these two parameters, that is, we need to remember this relation, S is equal to minus dg by dt at constant pressure, okay. So here, if this relationship can also be rewritten as, if I define a new parameter small s, that is equal to entropy per particle, basically and this is called as a specific parameter basically, or you can say that it's a specific entropy basically, okay. So then the relationship turns out to be equal to minus curly g by n upon dt at constant pressure, okay. Now this g by n parameter, either we can rewrite this as this is equal to minus d mu by dt, where mu is the chemical potential, okay, that's a Gibbs free energy per particle, or this can also be rewritten as S, that is equal to minus It's the specific Gibbs free energy. That's a Gibbs free energy per particle. Okay, so in that sense it become a specific quantity. Okay, and at constant pressure. Now, as we know that the entropy per particle, that is S small s, which is capital S by N, the entropy per particle, this is positive quantity. Okay, so if you just take a look at this equation, let's call this as equation 1. So entropy per particle, it's going to be a positive quantity, and here we can see that entropy per particle, that is equal to minus dg by dt. Okay, so therefore to make this quantity a positive quantity, dg by dt variation, that should be negative, that should have a negative slope basically. Okay, so that's a important point that we noticed from this basic discussion here. Okay, so therefore at least these two curves, the curve A, it's having when we are moving from liquid to vapor phase, so this curve is having a positive slope. Okay, so here to this curve, if you draw any line which is tangent, okay, so that will have a positive slope. The line will lie in the first quadrant. Okay, so therefore this is not the correct option. And if you just take a further look at the option D here, again liquid to vapor transition, again it's a positive slope here. You draw any line which is a tangent here, so this line will lie in the first quadrant, so again the positive slope. So that means this is also not the correct option. So now we are only left with two options, and we have to identify that which one of these two, B or C, which one of these two is correct here. Okay, so both here, when we are moving from liquid to vapor phase, both of these two curves, they have a negative slope. Okay, negative slope mean if you draw a line which is tangent to these curves. Okay, for instance these two lines, so these two lines, they lie in the second quadrant. Okay, so that's why they have a negative slope here, and here also a line, it's also in the second quadrant, and it's also in the second quadrant. Okay, so therefore in B and C, these two curves, they are having a negative slope. Okay, so the correct option will be either B or C. So let's try to understand how we can identify that point. The second point that we must note here is that the phase which is stable at higher temperature, phase which is stable at higher T or higher temperature will have higher entropy S. Okay, why higher entropy? Okay, so let's try to understand this point also, because the Gibbs free energy, that is given by H minus Ts. Okay, so the phase which is stable at higher temperature, we said that should have higher entropy, and if the stable phase is having higher entropy, so that means that is accompanied with the Gibbs free energy minimization. Okay, so therefore to minimize the Gibbs free energy, the phase which is going to be stable at higher temperature, that should have a higher entropy. Okay, so that makes sense. Okay, so that means if you just take a look at the picture B and C, so both of these two curves, again they satisfy this requirement also. Okay, when we are moving from liquid to phase boundary, the Gibbs free energy per particle, it's reducing. Okay, so that means again these two curves satisfy the condition 2 also. Okay, now then what is the meaning point on basis of that we can decide that B is correct or C is correct. Okay, the further important point that we should note here is that when we are moving from one phase to another phase, phase 1 to phase 2, at the transition point, the slope change occur. Okay, so that means when we are moving from liquid boundary to the solid boundary, from liquid phase to the vapor phase, there should be a change in slope. If you just take a look at the curve B, the curve goes smoothly here. Okay, and we do not encounter a significant change in the slope of this curve. But whereas when we take a look at the curve C here, so initially the slope, it's negative, of course. For the liquid phase, it's negative all the time. Okay, but here there is a sudden change in the slope of the vapor curve. Okay, so therefore this condition is satisfied, and the third condition is satisfied by the curve C. So therefore C is the correct option here.